Okay, so today we're going to talk about solving for the acceleration due to gravity on or near or somewhere away from Earth's surface. Okay? So acceleration due to gravity is given by what variable? No. We're going to look at how we can manipulate this gravitational force equation, the universal law of gravitation equation, to get to our acceleration due to gravity equation. Okay, so we're going to start with our first one, and we're going to assume that the mass, one of those masses is always the mass of the Earth. Okay, we're going to assume that one of those masses is always the mass of the Earth. Okay, because we're trying to find out what's the acceleration due to gravity at some certain distance from the Earth, right? So the Earth always has to be taken into account. Okay, so we just substituted m1 for mass of the Earth. Are we on the same page here so far? That's the only thing that we changed. Okay, we substituted on this side mass of the object times the acceleration due to gravity for Fg, right? Because anytime we're solving for the acceleration due to gravity, the gravitational force on the Earth, right, we do Fg equals mg. Would you agree? Right, that's something that we've learned already. So this gravitational force is for something that's on the Earth's surface, right? And we usually think of G as 9.8. But anyway, we're substituting this, and this mass is always going to be the mass of the object, right? Whatever it is that we're looking at. So we substituted this, which is why we called it M2, because it's not the mass of the Earth here. It's the mass of the object. The last step is just going to be to cancel M2 on either side. You have an M2 in the denominator on both sides, which means if you solve your algebra correctly, you should be able to cancel M2 on both sides. Okay, so to solve for the acceleration due to gravity, what's really the only thing that gets taken into account? The radius, right? The mass of the Earth doesn't change, G doesn't change. The only thing that really affects our acceleration due to gravity is the distance we are from the center of the Earth. Okay, so this bottom equation, which is a little covered up here, is one that we should have on our equation sheet. Okay, so G equals, little g equals big G times mass of the Earth over r squared. Okay. What do you think our radius here needs to be measured in? Meters. Has to be meters. Mass of the Earth has to be kilograms. Okay, so mass of the Earth you should have on your equation sheet already. That constant as well as big G. Okay. What do you think the units for little g will be? Acceleration due to gravity. Meters per second squared. Good. So you need to make sure you know the difference between Fg and little g. Right? One is a force, which is measured in newtons. One is an acceleration, measured in meters per second squared. So you need to know the difference between those two things because they don't mean the same thing. Right? They don't at all mean the same thing. Right? Okay, so let's look for the acceleration due to gravity on the top of Mount Everest, which is 8,848 meters above the Earth's surface. Okay, so above the Earth's surface tells us that we first have to add that height, right, that distance, to the radius of the Earth, because every radius we plug into this equation has to be from our object to the center of the Earth. So we always have to take into account the radius of the Earth there. Okay, so our radius would really be 6.38 times 10 to the 6th plus 8,848. So do you think this would be a good idea to round it back to 6.38 times 10 to the 6th? No, right? That's going to give us the on the surface of the Earth, right? So when you have this small distance, you have to be as exact as you can because we want to see the difference in the acceleration due to gravity. And it's not going to be a whole lot, right? You don't see things floating on the top of Mount Everest, right? You're still held to the ground, but there's going to be a slight difference. Okay, so little g is going to be big G times the mass of the Earth over r squared. Do not forget to square that radius. Okay, so what did we get, Morgan, for your acceleration due to gravity? What'd you have? Perfect. Do you think we should round up to 9.8? No, right? We want to see a noticeable difference, right? So 9.771, 9, you don't have to go farther than that, but you want to show that there is a slight difference. Do you think that that difference is noticeable when you get to the top of Mount Everest?
Nope.
No, right? You don't feel lighter, right? Things don't get lighter magically as you climb the mountain. There's other problems as you climb the mountain, but that's not one of them, okay? So you won't see a difference between that, okay? Okay, if the gravity on a hypothetical planet is 3.21 meters per second squared and the mass of the planet is 4.12 times 10 to the 21st, what's the radius of the planet? Okay, so the gravity on the surface of this hypothetical planet is 3.21. Are you going to use the mass of the Earth here, or do you think we're going to use the mass given to us?
Mass given.
We're going to use the mass given, okay? So it's the mass. These equations will work for any planet. That's why it's called the universal law of gravitation. So it will work for any planet. We just use Earth most of the time because that's what, we're used to, okay?
What's the long name for capital G?
The universal gravitational constant.
Okay.
Okay, so algebraically we're trying to get r here by itself. Okay, and don't forget to square root your r value at the end there since it's r squared. Okay, so algebraically what I did is I moved over g first, 3.21 divided by 6.67 times 10 to the negative 11th. Okay, then since my r is on the bottom, I'm going to switch those two places, so I'll take 4.12 times 10 to the 21st divided by that answer, and then I'll square root that. That's about what I have. Okay, so I move over g. You get it?
I divided. I took the 4.12 down.
Oh, okay. So once you're here, I just switch those two places. Yeah. Okay, so the next two we're getting are going to be satellite equations. So let me talk through them. You don't have to write them down while I'm talking, but these satellites, they orbit in uniform circular motion. So they go in a circular pattern, right? A circular path. And what is it that's holding the satellite in its path? Gravity, right? So not only do we have to combine our circular motion equations, but we have to work in our gravity equations too, right? Since gravity is what's keeping it in its circular path, we're going to assume that we have to use our gravity equation and our circular motion equation, so we're kind of combining these, okay? Uniform circular motion means that we're going to assume that they stay at the same height above the Earth the whole time. Okay, so if they're orbiting the Earth, right, here's the Earth, maybe. Okay, and here's my satellite. We're going to assume that it's going to be equidistant from the Earth at all times, right? It's not going to dip down or do anything crazy, right? We're going to assume that hopefully it's staying in its uniform circular path. Okay? So finding the speed of a satellite in circular orbit is this equation here. Velocity equals square root of g times m of the Earth over r. And you are more than welcome to walk through the derivation of that equation in your book if you really want to figure out where it came from. But I'm not going to do that right now. Okay? So velocity here is probably going to be measured in what? Good, meters per second. And this is a rare one in which our radius is not squared. Okay, so you just have to pay attention on which equation you're using. Okay, so that's finding its linear velocity, which is actually, like how fast it's really going. Okay, how many meters is it moving every second at that point? Okay, and then finding the period of a satellite in circular orbit around the Earth uses this equation. And tell me what the period means. What's period mean?
All like a full circle.
1 revolution.
Yeah, 1 revolution, and period means how long it takes. Right, how long it takes to make 1 revolution. Okay, and so even though it seems a little bit silly, period has to be measured in what? Seconds. Yep, has to be measured in seconds. Okay, in order for G to work, it's got to be meters per second squared, all that, all that type of stuff. So that's 2 pi. Must a satellite orbit in order to stay at the same point on the equator during its entire orbit? So this is called a geosynchronous satellite. Okay, which means it's going to stay. So if we had a satellite right above Topeka that we could see, we would be able to see it all the time because it's moving. Is it going to have to move as fast or faster or slower than the Earth? Faster, right? It's going to have to move faster because it's farther away. So in order for it to stay in our viewpoint, the whole time it's going to have to move faster than the Earth. Okay, so we're trying to find out what height above the Earth's surface does it have to orbit in order to stay there. Okay? So our goal is going to be to solve for r. Okay? We need to know the velocity of the satellite, and we know it's moving at the same period of the Earth, so that's how we can solve for the velocity. Right? If we know it takes the same amount of time to make 1 complete circle as the Earth does, that's what it means, it's going to be at the same point on the equator, we can find just solving the period of the Earth. Right? We know that T is equal to 24 hours, and we need to convert that to seconds. Okay. Oops, okay. I'm going to get rid of this stuff here so I got some more room to write. Okay, so we know the satellite takes 86,400 seconds to make 1 complete path. Okay, and our goal here is going to be to solve for the radius of that. Okay, what ideas do we have about how we could go about doing that? Okay, so what equation do we have for t? 2 pi times square root of r cubed over gme. Is that right? Okay, so this is kind of just a plug and chug here. R cubed over g times mass of the Earth. Make sure that when you move over that 2 pi, you either divide by 2, divide by pi, or you divide by parentheses 2 pi. Otherwise, you're going to start out your equation all wrong. Okay? So you're going to divide by 2 pi first. Okay, so from this step to this step, all I did was divide it over the 2 pi, and that's what I got. And then I also went ahead and multiplied these two down in the denominator. Okay? From there, what's going to be my next step algebraically? What do I have to do next?
Square root.
I don't want to square root.
Yeah, square
I want to square both sides. Okay, to get rid of that square root. Okay. From there, still to get r cubed by itself, I'm going to multiply these two together. And then, do you know how to cubed root something on your calculator? Okay.
There's no math.
Yeah, if you go to math, and then I think it's number 4, and then you can go second answer. So that means our radius is 4.226 times 10 to the, times 10 to the 7th. Okay, and is that our final answer? What's the one last thing we have to do?
You have to subtract the Earth's radius.
That's right. Since it says we want it above the Earth's surface, right now this radius, right, if here's our satellite, this radius goes from the center of the Earth to the object. And we only want this distance right here. So we need to subtract out the radius of the Earth. Okay, so minus 6.38 times 10 to the 6th. Okay, so solve now for velocity of that same satellite. When you use the radius here, what radius do you think you should use?
First one.
Yeah, the first one we found, right? The full one. Not the distance from the center or from the Earth's surface. You need to use the whole thing. So that 4.22 times 10 to the 7th. Make sure you're careful with that.
I found it cool.
I don't know what the heck you were
So,
doing.
Jake, what are you doing?
I don't know, he subtracted 4.22 or something.
Minus,